Okay, in today's lecture, we're going to try to put together a few things that we've done over the past few lectures. And one of the things to keep in mind is that in reacting systems, that you have endothermic and exothermic reactions. So this means that the products will leave at a different temperature than they come in normally, especially if you're operating the reactor adiabatically. And so there's a couple of ways to think about this and to take this into consideration. So if you sort of think about the beginning of a process, right, where, we're going to plot, let's just say we'll plot the temperature on the y-axis and we'll plot sort of the reaction coordinate on the x-axis. And you start at some initial temperature, right, before the reaction happens. And then after the reaction occurs, right, you've moved past that coordinate and the reactants leave at some other temperature, right? So it could be higher, it could be lower. I draw it as higher in this particular example. And so oftentimes what you'll see people do is take one of two pathways when they go through this. And the first thing that they might do is try to figure out what the enthalpy change would be if you were to have the reaction occur first. And then you would take the products and heat it up. And you would say that, okay, well, this would be delta H of reaction at the initial temperature. And then this would just be the integral of the products of, CPdT for all the products. And that red pathway could get you to the change in the enthalpy of the system. Well, identically, you could first heat the products, or heat the reactants, and then allow the reaction to happen at the higher temperature. So you could say, well, we could do the integral of CPdT of the reactants, and then you could do delta H of reaction at T final, whatever that is. And because enthalpy is a state function, either one of these should give you exactly the same answer. Now, I don't particularly like to do it this way because it's very rare that you really need to know delta H of reaction at the temperature. What you really need to know in our energy balance, remember, is that we have these terms that are the sum of the enthalpy in, right, which is a function of temperature and pressure, unless you're an ideal gas, of course, and then it's just a function of the temperature, times the molar flow rate or the mass flow rate in minus the sum of the enthalpy of the stuff that's leaving times the flow rate of the stuff that's leaving, either the molar or the mass flow rate. And so, in my opinion, sometimes it's really difficult for us to actually explicitly take these things into consideration if the first thing you want to do is to find delta H as a function of temperature and then worry about taking that into consideration and then heating the products. It seems to me like it's sort of a convoluted thing to do. So I'm not going to encourage you guys to do that when we do reacting problems. Instead, what we're going to actually do is understand that we have a reference against which every single reaction is judged, and that's the heat of formation for hydrogen gas, which by definition is equal to 0, and we talked about that in the last lecture. And so what that means is that every time that you have this H in or H out as a function of temperature, actually we can use the heat of formation of hydrogen as a reference. And the way that we can actually do that is that H in, we know, is then the heat of formation of whatever the species is at the initial temperature plus the integral from the initial temperature to the final temperature of Cp dt. So when it comes to actually solving reactor problems, I'm going to focus on using that particular method, okay? So I want you to be aware that that's where we're going. Now, there are some occasions where you do need delta H as a function of temperature. So I'm going to start class today by showing you really two ways to do that, right? To find delta H as a function of temperature. And then we're going to solve two example problems where we have to find the final temperature given some reaction is happening inside of our system. And when we do that, you're going to notice that I'm going to exclusively follow this method. And so hopefully I can talk you guys through it. The first one we'll be able to just do, sort of on pen and paper here. And then the second one will be a little bit more complicated, and we will have to use Excel, okay? So the first example problem that I want for us to solve today is one of these where we just need to find delta H of reaction. And we're going to do that for the combustion of hydrogen at 600 degrees C, okay? And of course, in order to do that, we're going to start with the assumption that we know the heats of formation at standard temperature and pressure. Of course, standard temperature is 25 degrees C or 298 K. So in order for us to do that, let's start by just deriving a couple simple expressions that we can use, okay? And so if everybody's on board that we're going to find delta H for the combustion of hydrogen, I'd actually like to bring my screen back, so that way we have a full screen of what I'm writing. And so we know that dH is equal to the integral of Cp dt from Ti to T final. And so we often think of this as enthalpy, but remember, I mean, this is really always a way for us to take changes of enthalpies into consideration. So instead of thinking about H, what if I said, well, the change in delta H of reaction then has to be equal to the integral from Ti to T final of the heat capacity change when a reaction happens times dt. And I'm actually going to end up defining delta Cp as equal to the sum of the stoichiometric coefficient for each species times the heat capacity of that species over I. And so if we look at this problem, well, then we have delta H of reaction at T final minus delta H of reaction at T initial, then equals just that integral. And of course, you remember that oftentimes the heat capacity is not reported explicitly like this, or at least not in tables, because they want you to be able to use the heat capacity equations regardless of the units that you're working in. So actually, what we really need is delta Cp over R. And of course, that means that we have to multiply here by R times dt, right? And the way that this is normally implemented is that we know in our book that the heat capacity for any species I is just equal to A plus BT plus CT squared plus dt cubed. And if you look at the way that that was defined, right, that delta Cp was the sum of the stoichiometric coefficients, we actually can use that to find that delta Cp for any reaction is just equal to delta A plus delta B times T plus delta CT squared plus delta T. And I apologize, I actually made a mistake. That's not how your book does it. That's over T squared. And so then that becomes delta D over T squared. Right? No, it is over T squared in the back of your book. Yeah, it's over T squared. And so each one of these deltas is essentially one of these relationships, right? So delta A would be equal to the stoichiometric coefficient times A, right? The sum of all of those stoichiometric coefficients times the A value. So the sum, and so delta B then would be equal to that times BI, and delta C would be the stoichiometric coefficient times CI, and delta D is equal to the stoichiometric coefficient times DI. And so one of the things then that we could do is that if we just insert that expression into here, right? And that's delta Cp, that's over R. Sorry about that, right? Because the back of your book defines delta Cp over R is equal to A plus BT. So we have delta Cp over R equals that polynomial. And so if we insert that above, then delta H of reaction at T final is just equal to delta H of reaction at the standard temperature and pressure plus, and then we just do this integral, which we've done before. That's R times delta A times T minus, or T final, minus our standard temperature, right? Plus delta B over 2 times T final squared minus the standard temperature squared, plus delta C over 3 times T final cubed minus the standard temperature cubed, minus delta D times 1 over T final minus 1 over T0, okay? And then end the brackets there. So one of the things that we could do is then use this equation to find the heat of reaction at a final temperature. And then of course we could always use that to compare to standard temperature and pressure. So our example, again, was to do this for the combustion of hydrogen. So let's think about this the way that we did last time, that the first thing that we really want to be able to do here is we want to understand the stoichiometry of that reaction. So we have hydrogen plus oxygen, and of course that goes to water. And if we want to balance that equation, right, there's 2 oxygens on the left, now we have 2 on the right, and now there's 4 hydrogens on the right, so now we have 4 hydrogens on the left. So it's 2 hydrogen plus oxygen gives us water, all right? And so I'm going to start what I did last time, and I'm going to make a table, right? And so I'm going to have species. I'm going to have the heat of formation of that species in joules per mole. I'm going to have the stoichiometric coefficient. And then the other thing that I'm going to do is I'm also then going to have A, B, C, and D from the appendices, okay? And so we have hydrogen, we have oxygen, and we have water. And since we're doing a combustion, I'm going to assume that that water product is in the gas phase. So the heat of formation, of course, for H2 is 0, for oxygen is 0, and for water, just like in the last lecture, this is 241,818 joules per mole. And then the stoichiometric coefficient for hydrogen, of course, then is -2, for oxygen is -1, and then for water is +2. And so then we can go back in the appendix and look for each of these A, B, C, and D values. So this is 3.249, 3.639, 3.470. B for hydrogen is 0.422 times 10 to the -3. For oxygen is 0.506 times 10 to the -3. For water is 1.450 times 10 to the -3. And then C for all of these is equal to 0. And then D for hydrogen is 8,300. For oxygen is -22,700. And for water is 12,100. Okay, so now we have everything that we need to solve this equation above. So I first want to do an example where I calculate one of these delta parameters. Okay, so let's do delta A, which I said was equal to the sum of the stoichiometric coefficient times A. So then delta A in this case would be the stoichiometric coefficient for hydrogen times the value for A of hydrogen, plus the stoichiometric coefficient for oxygen times A for oxygen, plus the stoichiometric coefficient for water times A for water. And so in this case, the stoichiometric coefficient for hydrogen is -2, then that's times 3.249, plus -1 times 3.639, plus 2 times 3.470. And then that value is -3.197, okay? And you can do the exact same thing for B, C, and D, where instead of having the value for A here, right, you would insert B, C, and D. And so delta B then equals 1.55 times 10 to the -3 delta C is of course equal to 0 because all of the initial values are equal to 0. And then delta D is equal to 30,300. Okay. So if we look at this and go back to our equation up here, that delta H of reaction at our final temperature is equal to the standard delta H plus all these different things. The only thing that we haven't yet calculated then is that value and of course the final temperature. So let's do that really quick and calculate the standard enthalpy of reaction. So then delta H at T0, that's equal to, right, the sum of the stoichiometric coefficient times the standard enthalpy. So again, for hydrogen, that's -2 times 0 plus -1 for oxygen times 0, then plus 2 times the value for water, which is -241,818, which is equal to -483,636 joules per mole. And so depending on if we want to keep this in joules or move to kilojoules, that's totally up to us. I guess we can leave it in joules per mole for a minute or two. Okay, so we now have everything on the right side of this equation, right? We have this, we've calculated all these delta values, and actually the final temperature we were interested was given in the problem statement, right? That we were interested in calculating the combustion of hydrogen at 600 degrees C, okay? And of course, 600 degrees C is 873.15 Kelvin. So I'm not going to write out this massive equation, right, where essentially we have delta H at T final plus delta H plus R times all of that stuff in the parentheses. But if you do that, you'll find that delta H at 873.15 Kelvin is equal to minus 493,939 joules per mole, right? Or minus 494 kilojoules per mole. Okay. All right. How is this? Does this make sense to everybody? You guys there?
Yeah.
Okay.
I'm still taking it all in.
Yeah.
Wait, could you explain one more time this how you got your final number?
Yeah, sure. I mean, so that number is from our equation here that we derived, that delta H at the final temperature was equal to delta H at our initial temperature, our standard temperature, right, at T0, plus R times delta A times T final minus T0, plus delta B over 2 times T final squared minus T initial squared, and so on. Okay. So yeah, if you think about it, what we did in the problem is that, first we calculated these values, right? And then we calculated this one, and then just applied this equation. Okay.
For R, did you just use 8.314 joules per?
Yeah. I mean, yeah. The only thing you really need to do is make sure that you match the units. So if you calculated delta H in kilojoules per mole, you have to use R in kilojoules per mole Kelvin. So the value that I happened to use, because I wanted to get my answer in joules at the end, was 8.314 joules per mole Kelvin. But one of the reasons to do it this way and to define the equation like that is you're completely free with the unit that you use. You just have to be consistent. All right, does that make sense?
Yeah, so your
Oh,
final number was your delta heat of reaction. You just
th-
didn't write it, so I was
there it is.
okay. Awesome,
Yeah,
thank you.
yeah. So that is delta H of reaction. Okay. So another approach that you could use is that remember that actually just delta H of reaction at any temperature is just equal to the sum of the stoichiometric coefficient times the heat of formation of all of the species at that temperature. So last lecture, we just assumed that we were at T0, right? So we wrote it like that, and we calculated all the standard enthalpies. So one of the things that you could do is to look at it from a heat of formation perspective. So you don't necessarily have to start off with, okay, I'm going to take delta H of reaction as delta CPDT. One of the things that I could do is I could automatically, or I could start by calculating the heat of formation at any given temperature. And of course, if you start from, delta H of formation is still just equal to the integral of CPDT, right? From T1, or the initial temperature, to the final temperature, or to keep the notation maybe the same, from T0 to T. And so, that means that the heat of formation at some higher temperature than minus the heat of formation at the standard temperature, right, is then equal to T0 to T of CPDT. And now essentially all that you need from this expression is, or from this equation, is some expression for the heat capacity as a function of temperature. So I'll do an example in a minute where we're going to actually use this approach, and we're just going to assume that it's a simple ideal gas, and then we know that this will be some multiple of R. But you could also take the temperature change into consideration and say that's equal to R times the integral from T0 to T of Cp over R dt. And the interesting thing is that this isn't fundamentally different than what you saw above, but the accounting becomes a little bit different. Like the math is all going to look the same, and you might think, well, how did we get to the same place from two different starting points? And it's because the approaches underneath are really very similar, but how you would do accounting is slightly different. And I like this method of accounting where I'm tracking the heat of formation of things that are entering and leaving the system as a function of temperature, because it allows me to do certain things, especially when we go to the Excel example, that's really complicated to take into consideration if what you're going to do is this and then try to implement that. Particularly when you don't know the final temperature, which we often don't. That's often the variable that we're solving for. So this equation, very similarly to above, says that the heat of formation at then any temperature is just the heat of formation at standard temperature, then plus R times the integral from T0 to T of Cp over R times dt. Now, of course, your book, we've already solved your book equation, and what you would do in solving a problem is that you would track these variables for each of the species individually, and then you might have a cell, that is specifically related to the heat of formation of, we'll call it, species A in a reaction. And then you'll have another cell at final temperature. And then you would have another cell that's the heat of formation of some species B at some final temperature. And then you would calculate those and then, subtract them or use them any way that we need to. And I'll show you how we'll do that when we actually start solving a problem. So you can use your book equation, okay, that Cp over R is equal to A plus BT plus CT squared plus D divided by T squared. That's also fine. So the other place that I really like, because they have a lot of additional data that I tend to use, and the fits tend to be a little bit more accurate and available over a much wider temperature range, is the NIST chemistry webbook. And you'll see in a second, I had flipped to that in one of our previous lectures very, very briefly. But for them, their heat capacity equation, as they say, CP is just equal to A plus B times T plus CT squared plus DT cubed plus E divided by T squared. And that T is not time, so that T is equal to the temperature in Kelvin divided by 1,000. And the expression is a little bit more complicated, but we'll see in a second, they actually do this same integral that we've been doing, and they get the heat of formation as a function of temperature minus the heat of formation, or the standard heat of formation is A times T plus B over 2 times T squared plus C over 3 times T cubed plus D over 4 times T to the 4th minus E over T plus F minus H. And essentially, that term ends up containing all of the T0 information. So remember, in our expression above, we end up with terms like C over 3 times T final minus T0 cubed, right? Those are cubed. Well, their expression here still has that part, but like C over 3 times this, and then B over 2 times T0 squared and all that stuff, that's all just buried in F. So they've already calculated that, and they just treat that as a constant. So if you're going to use the NIST chemistry webbook, don't worry about that. And then H here is almost always just equal to this number, the standard heat of formation. But there are times where you're taking the temperature range into consideration where they fit CP over R, and they have to correct for that you don't end up getting the standard heat of formation at the end. So we've looked at this before very, very briefly. And here's the NIST chemistry webbook page. So let's just look up, I think by formula, I have water. So, all right, so we'll have water. And actually, I didn't pick anything. So we'll do, we'll just pick some of the gas phase and liquid phase data for water, right? And that's H2O. And so here, if we scroll down, the first thing that the NIST chemistry webbook will give you is the gas phase data. So you'll get the standard heat of formation and the standard entropy of formation for that gas. And then we talked previously about the Stoichiometry equation. So you'll see here at the very, very top of the page where I have CP equals A plus B times T, et cetera. So I just wrote that a moment ago. And then the number below it, the enthalpy equation there, is just the integral, right? It's still just the integral of CP dt. But like I said, F has all of that sort of constant stuff in it. And then we'll also do some integrals related to the heat capacity when we get to entropy later on in this semester. And so then NIST will always have a table below that gives the temperature range that this is accurate to. And like I said, I like to use NIST because oftentimes in the back of your book, those fits have only been done to about 1500 Kelvin. Now we're going to do problems like one today where we're going to deal with a combustion. And it's totally possible in combustion problems that the final adiabatic flame temperature could be above 1500 Kelvin. And so suddenly you're going to solve a problem where the equation they use isn't valid. So, that's where something like this is helpful. And you'll also notice that water, for example, has 2 temperature ranges. So you will also, when we're solving problems, if you're going to use NIST for some of the higher temperature stuff, you'll have to take that into consideration, where your initial guess for a temperature might be 1000 Kelvin, but your answer is 2300 Kelvin. Well, obviously now the coefficients that you use have to change because the ones you started with here in the first column aren't valid outside of that temperature range. Because remember, they're just fitting this function, and functions can do absolutely crazy things when you get outside of the fitting range. All right, so I just want you to be aware of that. So we could always work through this problem again and show the exact same math that we just did a minute ago. But I'm not going to do that. What I will show is that I've done this, where for each one of these species, I've gone through for hydrogen, oxygen, and water and calculated the heat of formation at 600 degrees C, and I get the same answer. So you still get that this, the delta H, not that actually, that delta H of reaction at 600 degrees C is equal to minus, I got 493,939 joules per mole. And I mean, it's the same number, right, to 6 digits. So their fit in this case for these species, and at least picking the right temperature range, was very, very straightforward. So I don't expect you to do anything with this right this minute, but we're going to solve 2 example problems. The second one, having some awareness that the NIST webbook exists will be really helpful, and how that equation is implemented. And the same thing with the last homework problem. So if you guys have looked at the last homework problem, you might have thought, how in the world are we going to do this? We haven't done anything like that before. Well, that's what the next 2 examples are going to be in class. So if you're a little bit confused of how we're going to use that, that's fine. Just give me 20 minutes, and hopefully we're all on the same page by then, okay? So let's do this. Let's use these some heat of formation approach to actually solve a reaction-related problem, okay? So this problem says that as part of a long-running process, CO and air are fed to a well-insulated reactor. And in the reactor, the CO is combusted completely to CO2. The gases flowing into the reactor are at standard temperature and pressure, and you're asked to find what is the temperature of the gases leaving the reactor if the amount of air is sufficient to supply 100% excess oxygen. And you may assume that all the species are simple ideal gases. So I want to start the problem first, the same place that we've started problems several times, is that we have dnu dt is equal to Q plus W plus the sum of the enthalpy that's entering the reactor minus the sum of the enthalpy that's leaving the reactor plus 1/2 m dot times V leaving squared minus V, oh, sorry about that. Actually, it's in minus out. Entering squared minus the velocity that's leaving squared plus, I'm just going to write delta potential energy, because 1, I'm running out of space, and 2, you know in the problem you're told that you're not told anything about a change in height. So we know that's going to be equal to 0. Unless there's real extreme differences in velocity, right? This is going to go to 0. And you don't really expect there to be, because even if the temperature goes up a little bit and the number of moles of gas change slightly, that's not going to really impact the velocity a lot. In this chemical reactor, we're not going to cause anything to spin. We're not going to do any electrical work. We're not going to expand or allow the volume to change. So that's also 0, right? We're not doing any work. We're operating at steady state. And at least here, let's say that we're also adiabatic. So we're left with this expression, right, for the result of our energy balance, which will be really, really common, is that 0 is equal to the sum of the enthalpy that's leaving, and actually here, I'll write it the same way. I'll say entering, minus the enthalpy that's leaving. And in my notes, then I did an extra step where I just flipped the minus. So now the question is, what in the world are we going to do to account for these things, right? Or how are these going to get implemented during this process where we know that the molar flow rates are going to change? And we also know that we have to take the heat of, somehow take the enthalpy into consideration here. So here's what we're going to do, is that to track the changes in the molar flow rates, we're going to do something that you guys did in 300. So we're going to make an ice table, and we're going to use that to help us figure out and to account for, you know, changes in the number of moles. Okay, that's fine. And then for each one of these, we're going to use the heat of formation at whatever temperature that is. Okay, so let's first look at this reaction. So we have the combustion of CO. Let's balance that. So we know that we have CO plus O2 is going to give us CO2, right? And this is one of the rare combustions where you don't make water because this isn't a hydrocarbon, right? There's no hydrogens in the thing that's combusting. So this one's really easy, right? That's just 1/2 O2. And so then let's make something that looks like an ice table. I'm going to modify it slightly. I'm going to say, okay, let's look at species. We know we're going to need the standard heat of formation. So let's have that as a part of our table. And then let's build on this, right? So we have the initial, we have the change, and then we have the exit. And so we have CO, O2, because it's air, we have N2, and then of course we have CO2. And so the heat of formation for CO is minus 110,525. And of course for oxygen at 0, for nitrogen at 0, and for CO2 is minus 393,509. Now, here's where the problem gets slightly interesting, that we're not given an initial flow rate in, right? We know that it's flowing. We know that there's 100% excess oxygen, but how do we actually do this? Well, the easiest way is to assume a basis. And so we're just going to say that we're looking at 1 mole of CO2 per second, right? We could have picked anything, but this is a pretty easy one, right? So, and not CO2. I'm sorry, why would we feed CO2? We're going to feed CO. Sorry, guys, that was stupid. Okay, so we're going to feed 1 mole of CO per second, right? So that becomes 1. And now we have to figure out the flow rate for oxygen. So this says 100% excess oxygen. So to figure out what that means, you have to look at the stoichiometry. And a stoichiometric amount of oxygen would be equal to 0.5, right? Because you have, for every CO, you only need 1/2 of an oxygen. So the stoichiometric amount is 0.5. So 100% excess would be plus 0.5. So this is also then 1 mole per second. Now, if you think about air, right? So that's where the nitrogen is coming from. Feeding air, you have about a 4-to-1 ratio of nitrogen to oxygen. So really, it's 79 to 21 nitrogen to oxygen. But in a problem like this, where we're just trying to get a point across, let's just make the math easy. We'll call it 4-to-1, right? So then we have 4 moles of nitrogen, and we're not feeding any CO2 at the beginning. Now we're told in the problem that CO is combusted completely. So that means that the exit amount is equal to 0. That now the change in oxygen is minus 0.5. There's no change in nitrogen, right? Because it's inert. And then if you look at the reaction stoichiometry, for every mole of CO that is consumed, a mole of CO2 is created. So that's plus 1. And so then the exit for oxygen is then 1 minus 0.5, which is 0.5. For nitrogen, that's 4. And for CO2, that's equal to 1. Okay? So we have our ice table, right? We know the standard heats of formation for all of our species. So now let's actually implement this equation here, where we have that 0 is equal to the sum of the enthalpy that's leaving times the flow rate of the species that's leaving minus the sum of the enthalpy entering times the flow rate of the things that are coming in. Okay.
Dr. Mustaine,
Yeah.
could you explain how you got 1 initially for oxygen again?
Yeah, sure. Does someone want to jump in and help with that?
Isn't it because there's 100% excess oxygen? So since you already have 1/2 a mole, 100% more would be another 1/2 mole. So that's 1 mole total.
Yeah, that's right. Yeah, from the stoichiometry. Thank you very much. So from the stoichiometry, for every 1 mole of CO that you put here, well, that's really messy. Sorry, guys. You only need 0.5 moles of oxygen, right? From the stoichiometry. And so if you're going to give 100% excess, then you need to add 0.5 more, right? And 200% excess would be +1, and 300% excess would be +1.5. All right, does that make sense?
Yeah, thank you.
All right, no problem. All right, so now let's actually implement that equation, right? That 0, and I'm gonna slide this over so we can have a little bit of room to work here. So then 0 has to equal, let's see if I can maybe slightly, it's too far away. Sorry about that, guys. So now we're gonna account for everything that is leaving minus the stuff that is coming in. So think about what is it that's leaving. So we have the molar flow rate of oxygen leaving times the heat of formation of oxygen at the final temperature, which is the thing that we're trying to solve for, right? Then that's plus the number of moles of nitrogen times the heat of formation of nitrogen at the final temperature, plus the number of moles of CO2 that are leaving times the heat of formation of CO2 at the final temperature, right? So this is all the stuff that's out. So this term is just the sum of the enthalpy out times the flow rate leaving, right? That's what this term is. So then we have to then subtract the equivalent term of the things that are entering the system. And so then that is the molar flow rate of CO times, since we start this at the beginning, right, we said we fed everything at atmospheric temperature and pressure. So that's just the standard heat of formation. Then that is plus the other thing that's entering, which is oxygen. So that is the number of moles of oxygen entering times the standard heat of formation for oxygen, plus the number of moles of nitrogen that are entering times the standard heat of formation for nitrogen, right? And that's our energy balance. That's the sum of H out, M dot out, minus the sum of H in, M dot in, okay? And before I do anything else, I just want to make sure that everybody sees that that's true. Okay, with no objections, all right, I'll keep going, but hopefully that's obvious. So if that's true, then let's solve this, right? The only thing that we really don't know is this final temperature. So the first thing we're going to do is that we know that the heat of formation, the standard heat of formation for oxygen is 0, and the standard heat of formation for nitrogen is also equal to 0. Okay, so we know that we're not going to have to account for those terms in this particular problem. All right, so then 0 equals then the number of moles of oxygen times the heat of formation of oxygen. Now, remember, the heat of formation is equal to the standard heat of formation plus the integral of Cp dt from T initial to T final, right? So for oxygen, the standard heat of formation is just equal to 0. So now for oxygen, all that we're left with is that particular term, right? This integral of Cp dt. And since the heat capacity is equal to a constant, we actually can just make that Cp times delta T. So this becomes the number of moles of oxygen times, we'll call it Cp oxygen, times T final minus T0, right? Or the standard temperature. And you can do the same thing for nitrogen because the standard heat of formation for nitrogen is also equal to 0. So this is the number of moles, and that is out, just to account for this correctly. So that's the number of moles of nitrogen times the heat capacity for nitrogen times T final minus T out, then plus the number of moles of CO2 that are leaving times the heat of formation for CO2. But remember, the heat of formation for CO2 is not 0. So this becomes H naught CO2 plus then Cp dt, or Cp for CO2 times T final minus T0. Okay, and all I've done so far is sort of expand on that a little bit. And then of course, then that's minus, and all that's left here is the number of moles of CO plus, here maybe I'll do this, times the number of moles of CO, then times the standard heat of formation for CO, right? Because this is just that number, right? Because it's entering. All right, so now we can actually solve this problem. So we know then that 0 equals, so the number of moles of oxygen that are entering, we calculated to be 0.5 moles per second times the heat capacity for oxygen, which is just 7/2 times R. So 7/2 times 8.314 joules per mole Kelvin times T final minus 298.15 Kelvin plus the number of moles of nitrogen. So that's 4 moles per second times the heat capacity for nitrogen. And that's also a diatomic simple ideal gas. So that's also 7/2 times 8.314 joules per mole Kelvin times T final minus 298.15 Kelvin, right? And then plus the number of moles of CO2, which is 1.0 moles per second, times the heat, the standard heat of formation, which is minus 393.509 joules per mole of CO, then plus Cp delta T. And of course, since this is a triatomic gas, Cp is 9/2 times R times T final minus 298.15 Kelvin, right? So that's this first term of the stuff that is leaving, and then minus the stuff that's entering, and that's just 1.0 moles per second of CO times the heat of formation for CO, which is minus 110,525 joules per mole. Okay, and our unknown is here, here, and here, right? So you could rearrange this, right? Or you could just use goal-seek in Excel, which is what I did, and you'll find that the final temperature is equal to 1979 Kelvin, which, if you want that in Celsius, is 1706 degrees C. Okay, so that's pretty hot. All right, so does anybody have any questions? Okay, all right, so if you're able to stay, let's move forward. And this example says that you're going to light a natural gas fireplace. And assuming that the fireplace has a 300% excess of oxygen of air, right, that enters the fireplace as this combustion is happening, calculate the temperature of the gas leaving the chimney. You can assume that no heat is lost through the chimney walls, and also assume that natural gas is 100% methane and that the combustion goes to completion. Okay, so, our system, if we want to think about it that way, is that we have some fireplace, right? And we have some flow rate of natural gas that's coming in, right? And let's say it's being supplied at standard temperature and pressure, and then we also have some flow rate of air that's coming into the system, we're also going to assume that it's at standard temperature and pressure. And so what we're really asked to find is, the flow rates that are leaving and the temperature that's leaving. Okay. And so the place that I would start is very similar to where we started the last problem, right? Where we had this ice table, okay? And we know from a previous lecture that if we're going to balance the equation for the combustion of methane, there's methane plus 2 oxygens gives us CO2 plus 2 water molecules, right? So if we put that into our ice table, so we're going to have species, and then we'll have the inlet concentration, we'll have the change, or the inlet flow rate, not really the concentration, and then we'll also have the exit. And you notice I didn't put the heat of formation here, and that's because we're going to automate this in Excel this time, as opposed to trying to solve for this by hand. So we will flip over to Excel at some point and try to explain exactly what we're doing. So then here's methane, oxygen, nitrogen, CO2, and water, right? So each of these species participates in the reaction except for nitrogen, right? Because we're told that we have air. So, all right, we're in the same position that we were in the previous problem, where we're not given an inlet flow rate. So I assumed one. I assumed a basis of 1 mole per minute of methane, all right? And, the time element actually doesn't matter at all. We're just using this number. And so, right, that becomes 1. And now if you try to think about this, we have 300% excess oxygen. So if we look at the stoichiometry, that if you started with 1 mole of methane, the stoichiometric amount that you need is 2. But 300% excess is 3 more of those, right? 2, 2, and 2. So that means that 300% excess is actually 8 moles per minute of oxygen. And remember, air is about 4 to 1, so that's 32 moles per minute of nitrogen. And there's not a lot of CO2 in the air, right? I mean, I'm not going to track, when we're talking 8 moles per minute, I'm not going to track 400 ppm CO2. So that's effectively 0. And the same thing with water, that we live at pretty moderate temperatures and the humidity is not usually crazy. So, we'll assume that the air coming in has a very, very low water content as well. So now if we follow this reaction stoichiometry, you would expect that if you fed methane on a flame in a fireplace, that you would consume essentially all of it. So this is going to be -1. From the reaction stoichiometry, that's -2. That's 0, right? Because nitrogen doesn't react, at least not in this case. We're not considering it. And then that's +1. And then water, of course, then is +2. So that means leaving our system, we have no methane. We have 6 moles of oxygen. We have 32 moles of nitrogen. We have 1 mole per minute of CO2. And then we have 2 moles per minute of water, okay? And our energy balance should be exactly the same as it was in our previous problem, right? Because we have an adiabatic reactor where we're not doing any work. It's operating at steady state. So we get to the same place we just were a second ago, that our energy balance is 0 as the sum of the enthalpy out times the mass flow rate out minus the sum of the enthalpy in times the mass flow rates that are entering the system, okay? And just like in the previous problem, we used the ice table for those, and just like the previous problem, that we are going to use the heats of formation to describe the things that are entering the system and leaving the system. The only difference is that this time I'm going to implement this in Excel and to show you what that might look like to do this in an organized way. But we're still going to implement the exact same equations here, right? The heat of formation is still equal to the heat of formation at, and here let me be a little bit more specific about this, that the heat of formation at an elevated temperature is still the heat of formation at the standard temperature plus the integral of CPdT from T0 to T. And now when I do this in Excel, I'm actually going to use NIST values. So you guys can also see what that's like, because if you remember the last problem, we had a combustion, the final temperature was 1700 degrees C, right? And so it's possible that the answer to this problem or the answer to the homework problem could fall out of the range that your book actually is able to provide. So let's flip over from here to Excel, and I'll try to talk you through exactly how I implemented it. And also now you'll have this conversation as you solve your problem in the homework, that you could use this as a reference case. So you could see if your Excel spreadsheet, which I'm certain for that problem that you guys will need, is behaving the same way that mine is here. Okay, so in this particular problem, here's how I set this up. That at the very top of the sheet, I have all of the species that we have to account for in this problem, right? Here's methane. Let's see. Okay, so there's methane, CO2. You notice that we have 3 lines for oxygen, right? And each of them are in a different temperature range because I didn't know where the final temperature was going to end up the first time that I solved this problem. So I made sure I had all the coefficients here. I have water, and then I also have 2 lines for nitrogen. So I have all 5 species, but I have more than 5 rows. So just to keep that in mind. I've also here reproduced the equations that they gave us in the NIST chemistry webbook, where the heat of formation at some elevated temperature is equal to, right, the standard heat of formation, or minus the standard heat of formation, equals A times T plus BT squared plus CT cubed over 3 plus DT to the 4th over 4 minus E over T plus F minus H. So really my task then in this problem is to find a way to intelligently implement this problem, right? How do I do this in a way that lets me change that temperature freely and then have the values calculated every time that I change the temperature? So that's actually what I'm going to show you what I did. So the table at the top is only values. So then the table in the bottom, and I'm just going to scroll to that really quick so we can go through it, is just the ICE table, really, if you think about it, that's implemented slightly differently. So here's our initial conditions. So these first 3 rows in my sheet all deal with the inlet. And then these last 3 rows all deal with what's going on at the outlet. And I've tried to implement the mole balance and calculating the enthalpy using those equations from the NIST chemistry webbook. And the first column, or sorry, the first row here is essentially just calculations. So our initial condition is 25 degrees C, which is 298.15 Kelvin. And then I use the equation above, which of course these all should just be the standard values, but I wanted to check that. And that's a really important thing to do when you're implementing complicated equations, is that we know what these values should all be, right? Because we have them, they're all tabulated here, right? We know what the standard heat of formation should be. So let's make sure that when we insert the standard temperature, that we actually get all of those values back from the equations that we use. And that makes sure that when we move to higher temperatures, we didn't make some silly mistake. All right, so there's our, in each column is a different calculation. So there's the temperature input in degrees C, and there's Kelvin. Then I converted that to Kelvin over 1,000 for the NIST equation, just like we talked about a little while ago. And then I use that to calculate the enthalpy of formation at the standard condition, okay? So you'll notice that oxygen is essentially 0, nitrogen's essentially 0, and the other ones are very close to their standard heats of formation in the table. All right, so then the second row here is the flows. So remember, we chose a basis for methane equal to 1 mole per minute, and then oxygen was 8, nitrogen was 32, and everything else was 0. So in our energy balance, we then have these terms that are the sum of H in m dot in, right? So what I've done in Excel is the first thing I've done is for every pair, I've found this value. So you don't have to do it this way, but this is the way that I chose to do it. So for me, you'll see that there's just 74 times 1, right? Which is just H in m dot in for one term, right, for methane. And I do the same thing for all of these, right? And so then for me, when I solve this problem, then what I'll do is I'll take each one of those, like all of these cells, and I sum them in that cell. And what that means is that in my spreadsheet, this cell is just the sum of H in m dot in. Okay, it's just the sum of these. Okay, and then I did the same thing with the exit. So for the exit, I have an initial guess for the temperature, right? This is the value we're trying to find, but we don't know what it is. And you can't leave a blank, because when we use goal-seek in a minute, you're going to have to provide an initial guess that the program is going to iterate from. So I said, look, it's going to be higher. I don't know how much higher. So I guess 400 degrees C, which then the same thing happens. So now at 673, the program converts the temperature to Kelvin over 1,000. Then it calculates the enthalpy for methane, oxygen, water, CO2, and nitrogen, right? These are all the heats of formation at the guessed temperature. And then I've implemented my mole balance here. So that's 0, right? That was 6 after the reaction. Then that's 2, that's 1, that's 32. And remember, we also have the sum of H out times m dot out. And so each one of these terms, just like above, is each one of those cells. And then I sum those cells over here on the right. So that cell is just the sum of H out times m dot out at my guessed temperature. So now my energy balance, of course, is just that this thing in green minus this thing in blue is equal to 0. And you can see at the guess temperature, right? This is our energy balance. And at our initial guess, we're wrong. And that's not incredibly surprising, right? It would be a shock if your guess temperature was totally correct. So here's where in a spreadsheet like this, we could use goal-seek. Right now, the iPad version of Excel doesn't run macros, so you can't actually do that. But one of the things that I could do here is to change the temperature if it's going to let me do that, right? And so let's insert, when I ran this before, it was like 650-ish, okay? And now you'll look that our energy balance is now approximately equal to 0 with this new temperature. So our exit temperature in this chimney is, of the gas that's leaving the chimney, is about 650 degrees C, or 923.22 Kelvin. And where your problem in the homework is going to really differ is that it's going to ask you to change this. So quite frankly, this is a good base case for that homework problem, where now it's going to tell you, well, what if you fed different percent excess of air? We made an assumption here that it was 300% excess air. What if it was 100% excess or 50% excess? Well, now you're flowing a lot less nitrogen through. So you might expect the temperature should be much higher. It also says, what if you used oxygen and excess oxygen instead of air, where now you don't have to carry the nitrogen at all, and you would expect that temperature to be really, really high. So, that's how you're going to implement what we've been doing today in the homework problem. You also could do other interesting things in a problem like this. Like we could raise the assumption or erase the assumption that you're operating adiabatically. So what if we said, well, if you were running a real fireplace that was at this flow rate, I calculated it, it's about a 50,000 BTU per hour fireplace, which you can buy, actually. You can buy a 50,000 BTU per hour fireplace. So let's say that you lost half of that heat. So that would be minus 25,000, right? And in doing that, we just change the energy balance a little bit, right? It's that now minus Q, or 0, equals Q plus the sum of delta H in minus delta H out. And so now when we lose heat, you can see obviously this energy balance doesn't balance anymore. And you would then expect the temperature leaving to be lower than it was initially, right? Because we're losing a bunch of that. And so when I ran this earlier in GoalSeek, that was equal to 317.96 or so. And you can see now the energy balance is once again equal to 0. So we found the correct temperature.